What are we looking at? Anyone? A planet, good. So that is the surface, yeah, surface of something. Some craters.
Wait.
Some craters.
Well, there's volcanism.
I think there's volcanism. Interesting. Why do you say that? What do you say?
New flow.
New flows. So that can only be volcanoes, right?
Oh, I guess other things flat.
Other things could flow. But in fact, it is volcanism. Where is this volcanism? Thank you.
Alright,
Is it underground? Nope. What planet are we looking at? Mercury. Nope.
Venus?
Does Mercury have volcanism on its surface?
Oh, no.
No, definitely not active.
Venus?
This is Venus. So if you're on science Twitter, which I don't expect you to be, this came out today. Whenever I teach this class, I always like try and throw fun new things. So this is the most recent version of volcanism that they've seen, active volcanism on the surface. Now, when we say active volcanism, we have to be a little careful because what?
Would that be like today?
Yes, yeah. So that's the question, right? As soon as I started reading the press release, I was like, well, the pictures are from 1991. So
The finding came out.
but the finding came out today. So it turns out someone was really bored during Zoom calls and decided to start looking through the Magellan data set, which was taken in 1991. And they just were like looking and they're like, huh, that kind of looks different in these two pictures. And they did that a bunch of times and they found like this whole region in which active volcanism was existing in 1991. Now, in a geologic time sense, that's right now, right? Geology doesn't change over the 20, 30-year time periods, except for like massive erosive features. But for volcanism, ongoing volcanism is, in the past 10, 50,000 years, not 30 years, right? So we call this active volcanism. This is direct evidence. Before we had inferred evidence of volcanism by looking at emission, like heat on a volcano and saying, it's probably likely that there's a volcano there. This is direct evidence. Because in fact, this is a vent that's creating a magnetic flow and that's covering up our good old friend, the crater. Okay. Breaking news. And then I was like, my friend who's a planetary scientist sent me like a chain, these like chain letters with all of the emojis in them. It's like a science one. It's like slightly inappropriate, so I won't show it while it's being recorded. But if you're curious, I'll send it to you so you can send it to your friends. It's pretty funny. Okay, questions before we get started today? You're turning in homework 4. If you haven't picked up your homeworks here, let me know. I know that I'm still getting through them. I promise we'll get up to date by this weekend. And you'll see your weighted score, which we talked about on Monday. Yeah.
Can I ask what the weighted score is? Is that like our overall total?
Yeah. And you can compare that to what's in the syllabus for whatever your letter grade will be. If you see a 0 somewhere, that just means I don't have that from you. If you weren't there, fine. That's a 0. If you were there, you need to give it to me. Okay? Everyone happy? Okay. So we talked about okay. Why? Why isn't this working? Okay, we talked about the greenhouse effect. What's the example we use for the greenhouse effect? Your car. So light comes in, heats up your warm leather seats. They warm up the air inside the car. And now it's infrared light is unable to get out. And so it stays trapped in your car and it heats up your car and then it burns, right? Why is this? I'm gonna scream. What does the greenhousing? Water vapor is one form of the greenhouse effect. Anything else? What's that? Methane from cow farts specifically? And the one that we're making right now, thank you everyone, CO2. Not just from our mouths, but most importantly from the over industrialization of the world. Okay. Okay, so we talked about, I don't know, do I just have to stand here like an idiot now? Okay, so we talked about, hold on, let me just stop this and we'll do it again because I don't know what's happening here. Driving me insane. There we go. All right. So we talked about that the Earth's atmospheric content is mostly nitrogen, and in fact, not very much CO2. Why is it mostly nitrogen and oxygen? Does anyone know what happens to the CO2? Yes. Plants. Very, very important that plants convert that CO2 into something that we can breathe. Okay. And the concentrations of those atmospheric gases that you see there are very small. They're trace amounts. They're very important. Water is the dominant greenhouse gas on Earth. If you remove water from Earth, what happens to the temperature of the atmosphere? It goes down. You remove water and you keep oxygen, you keep everything else, you will not have a greenhouse gas. You remove greenhouse gas, it's like opening the sunroof in your car and the hot air goes out. Heat goes out. Does that make sense? Okay. Compare this to Venus. It's mostly CO2. Not surprising why our nearest neighbor is very warm. Okay. Finally, Mars has a lot of CO2 as well, but got a wimpy atmosphere. So the total effect is very negative. Okay. Okay, so which of the following is a part of the Earth's natural greenhouse effect? Is it A, the Earth's atmosphere continually becomes thicker with greenhouse gases? B, infrared light permanently trapped in our atmosphere by greenhouse gases? C, the ozone hole causes significant increases in surface temperature? D, Earth's surface and atmospheric gases absorb energy and then give off infrared light? E, heat is transferred in the atmosphere through the circulation of greenhouse gases. When you're ready. This. Then let's vote on 3, 2, 1. Okay. How many we got here? That's oh, this is a really nice variety. All right, turn to your partner, someone who doesn't have the same answer as you, and try to convince them what you got. You ready to revote? How do you feel? More confused, less confused? For this side? About the same. Same confused? Let's revote on 3, 2, 1. Okay, okay. All right, anyone want to defend their answer? Someone who got convinced by a friend? No one got convinced, even though most of your answers went in one direction. You have nothing to lose.
That's right.
Your pride, this is a learning example, yeah.
So I went with, four.
Okay.
The way I remembered, I thought of it as like each layer of Earth's atmosphere was absorbing like a specific, type of light.
Mhm.
And then when it got down to Earth's, surface, that was the only one that was emitting infrared. So
Right.
like it was generating heat from that.
Right. Okay, I like that idea. Yeah, so this says the surface and atmospheric gases absorb energy and then give off infrared light. We know the surface gives off infrared light because it's hot. And then there are atmospheric gases, like we said, water, for example, likes to absorb and then re-emit infrared light. So that makes sense. So which ones don't make sense here? So the atmosphere does not continually become thicker with greenhouse gases. We are making some, but they get broken apart on long time scales. Infrared light does become trapped, but not permanently. Okay, that does eventually leak out. The ozone hole doesn't do this. That's not the purpose. Well, okay, no, you're right. It causes insignificant changes in the surface temperature, but only over a small portion of the planet, and that happens to be the South Pole. So we said that one, and then heat is transferred to the atmosphere through circulation of the greenhouse gases. It's not the circulation that transfers it, it's just their presence. You put greenhouse gases, you trap heat. Okay? So we get this concept now? Okay. So we're gonna add these two things together because we talked about imagining a theoretical planet. And perhaps we'll do this in, say, a homework that I assigned today. We're gonna think about a theoretical planet. And we play with these funny ideas of distance from the sun, of size, and of rotation rate. And so we think about, in the absence of greenhouse gases, the surface temperature does not depend on the size. Unless it's like a magma surface. That's not usually common. The distance from the sun definitely is important, because as I get closer, it gets warmer, right? And whether there's a rotation rate, the average kind of evens out, right? If I add greenhouse gases, how does this change? Which of these are become more or less important? Rotation is, again, we're still thinking about average. Yeah, the distance becomes really important. Because now if I get closer, I add more visible light, I heat up the surface more, and I have greenhouse gases, that's gonna become a problem quickly, right? Okay. Another thing we can add here is reflectivity. Another word for that is albedo. What does this word reflectivity mean? Yeah, perfect. So how much light you can reflect? Great, no trick there. What's an example of a low reflectivity? Say in this room. The desks? Yeah, not very reflective. I can kind of see it. I mean, they're dark. There's a better version. Is this more or less reflective than other things in the room? What's the least reflective thing you can see in this room? Me?
No.
Well, like the edges of the screen.
Ooh, that's very good. Yeah, that's, look at how much light it absorbs. See, reflection gets rid of almost all of it. That's pretty good. I would go even with stuff like the black clothing in this room. It's probably pretty absorptive, not very reflective. What are good examples of high reflectivity objects? Don't say lights. Phone surfaces? Yeah, not the backs, right? Is that reflection or is that a different project?
Never mind. The floor, that's all.
The floor is also very reflective. I'd be getting light off of it. Anything else?
Not the floor.
The clock glass. The clock glass is actually not reflective.
The one that's even on it.
It's kind of reflective, but it's not reflective. If I were to instead to, here's an interesting thought experiment. If I take the glass and I move it, if I move if I move the hard plastic away from the back. Right, there,
Can you see through?
would you be able to see through it, or would it still have that glare?
It has
Well,
glare.
Mostly see through.
What about the environment like that? Like
And I would just go with like light stuff, or why do we make the roofs white in places?
They don't want to pay to
Bounce light, so that it comes back down.
Yeah.
You don't want it to be black, right? That's gonna make a room feel really dark, very inclusive. Kind of cool, okay, well, you can do that at home. So yeah, so anything that you can see that's very reflective, right, that's good. When you think of clouds, or you go skiing, you wear sunglasses sometimes, you get snow blindness. Has everyone had that before? Ever been in snow? And you get like a sunburn like here, you're like, what the fuck? All the light reflects off the snow and burns your face if you're not wearing a.
Like when it's snowing or after?
After.
Or
Oh,
like
no.
when you go to the beach and like the water. Reflects off.
Yeah, waters are reflective too. Yeah. So we call these measures of reflectivity, we call it the albedo. And this is a measure that's gonna go between 0 and 1. If I absorb all of the light, I'll call that albedo 0. If I reflect all of the light, I'll call that albedo 1. Okay, simple math, right? On average, what do you think the albedo of something like dirt is? Is it half? Is it a quarter? Dirt?
Like it's 0.
Well, you see dirt, right? It's gotta reflect sunlight.
Oh,
Well,
doesn't mean
0
like
is-
0.
So 0 was no reflection at all, absorbing all light. And 1 was all reflection, no absorption. So most objects are not going to be at either side, right? Because in fact, we see most objects. If something absorbed all the light, you wouldn't see it. You would just see it moving and blocking things out. Air.
Aliens.
Okay, so what's an example of, say, dirt albedo? What would you guess? Half, you think half? Anyone else?
Third.
A third? Okay. What about snow? Close to 1? Okay, all right. We're gonna come back to this a little bit. But I wanna know right away.
Yeah.
Okay. And so of course, this really matters. Planetary temperatures, for example, really matter on the albedo. Okay. So what would happen to Earth's temperature if it was completely covered in fluffy white nitrogen clouds? But still have the same amount of greenhouse gases as it does now. Would A, the temperature go up, getting warmer? B, the temperature go down, colder? Or C, the temperature would not change? Next question.
Oh, higher than clouds.
Good question.
Oh, it's good.
Let's imagine that they're like standard clouds in the troposphere. Let me know when you're ready. Let's vote on 3, 2, 1. Okay, we got every answer. Let's go. Okay, so what do we think it is and why?
I'm just thinking it's humid when it's super cloudy.
Okay. Humid when it's super cloudy, we're thinking about it in the context of our personal experience. Okay. But what about in the context of what we're talking about? Or not necessarily nitrogen, just fluffy. I'm thinking fluffy white clouds. Maybe in the context of like this concept. Yeah.
Pick A, because I feel like it would just keep bouncing light up and down, just making it hotter. Yes.
Okay, okay. Anything else?
I thought it was interesting, because like, don't we have? It was, like, it's like how air goes, the hot air goes up, and it's like,
Oh, like circulation in the atmosphere?
so that's why I thought it was just the circulation in the same spot.
Okay.
You know what I mean?
Okay. Yeah. No, it's not a bad explanation. We're gathering all the ideas, we're gonna put them apart.
Cut the light when it bounce off, so that when it put the light to warm it up, so I think.
Get colder. Any other ideas? Okay. So we talked about the effects of an atmosphere. Okay, you have light that comes in. You have light that gets absorbed in the atmosphere. You have light that gets scattered. So this is what makes the sky blue. And you have some reflection from clouds. The reflection from clouds is going to stop it from being transmitted all the way to the surface and being absorbed in the surface. But it does, in fact, really matter how high the clouds are. So if I have really low clouds and most of that light makes it down to the surface, you might have a different effect than if you have really thick clouds very high up. Why is that? Because if those clouds are really far down, like this, okay, they're going to create a little blanket, reflect everything off, okay, and it's going to make us nice and cold. They're higher up, you get a little blanket here where you still have heat from the surface, but now it can't get out because it's being trapped by clouds above it. So you can think about it in both ways. And in fact, these are very complicated effects. If you set at all three of these answers, you're right in one way. So it can both not change at all, it can make it warmer, and it can make it colder. Atmospheric scientists hate clouds. They're very annoying. Okay. On the other side here, you have infrared. This is your form of loss. And so you can have scattering in the lower atmosphere, and clouds are really good scatterers. Their ability to reflect both infrared and visible light is remarkable. That's why they look white, right? They're scattering all of the light. You don't have blue clouds, right, that just absorb the red. You don't have red clouds, they're white. They just scatter everything and they don't care. So if you put a bunch of clouds in here, you're going to distort how all the emission of infrared light is able to escape. And in fact, when we look at planets, there's a strong coupling between the dynamics of the atmosphere and the appearance of clouds. Okay. And then some of it gets out and that cools the planet. That's really important that the heat gets out, because if the heat doesn't get out, the whole atmosphere cooks you alive, right? Because the heat coming in from the sun is constant. And so you need to be losing that heat in one way or another. So if this is not balanced, in versus out, the temperatures keep going up and up and up. Okay. So when we think about global climate change, and we'll talk about this a little bit in detail, what's the reason for climate change? Greenhouse gases, yeah, but in the math that I just showed you here. More sunlight in than can get out, because we trapped it stupidly, and we're getting warmer. Okay, it's that simple. So it's really not our fault. It's the sun's fault. We're just turning the sun down a little bit. We're turning it down to 9 or 8, and we'll be chill, right? Freaking sun. And in fact, some people very seriously have considered the effects of just aerosolizing small pieces of silver and sticking these into the top of the atmosphere to make our planetary albedo go up. Be extremely expensive, but it would work. It's an idea. An idea called cloud seeding. Okay, so in general, we talk about planets this way. We showed this already before, right? You have the visible sunlight in. You have the emission of the planet here, right? What planet was this? Mars. And you can tell from the variety of features, including the fact that it's missing blue, and it's showing up in red. You can almost see the albedo here, right? The reflectivity is certainly not 1, but it's also not 0. So it's like 60, 70%. Water is mostly 70% of the atmosphere, the Earth. So here, this is rock. I don't know, you can do some math there. You see CO2 bands? here. You see emission lines here. Right? These CO2 bands, they are the ones that are causing that. Really, really annoying. Okay. We're gonna talk about the greenhouse effect in a lot of detail here. When we talk about the distribution of energy from the sun and how it's absorbed. Okay? Is that it? Sleep? No. Okay, so make a new friend. No, you just have to get people who don't have. Mix you together. So there's like an odd number of people on this side and an odd number of people on that side. Yes. Oh. Yay, thank you. Yay, thank
Yes.
Yes, yes. Yeah.
And I'm looking at it, like, right. Going back and forth, I'm like, what? So I was putting in image before, but now it's very like. Really hard to stop.
Yeah. A very old.
Like, you're like, ready to let it. It's just very much. Yes.
Election story.
The lab.
Guess what?
Feels like a lab.
It's easy.
So many pages.
We love learning in this class. That's why we want more pages of lectures for
I'm just like, I can't read.
it. I can read it to you guys.
No.
No, no, that's okay.
They struggle. More, or I don't care how much it figures out, it doesn't matter how much it figures out. The part of it that, there's a whole. So even if it's even out, whatever. Yeah. So, and then, like, this, like, okay. Yeah.
That's like, yeah. But each.
Or. Girl and that's good. Yeah. Yeah, and that's the fact that I have. Do that in words. You're saying that. Yeah. Yeah.
I need to go back to.
No.
It's hard to say, recently I got into the show again, production. Oh, yeah, well, it's a lot better than like. But that's so close to LA. So many like record executives are coming out, and, like how it's got that you get, high quality. And the variety is they cultivate artists and genres. So you have like hip hop stations next to or all the rock next to pop next to I know. It's not the journey for us. Do it. It's April. It's fine. It's like a month before. I was gonna use my birthday. That's like, yeah, my birthday's May 19th, so it's been almost every year. I'm gonna be happy you'll never run. There's only one reason to do that. Last year we had an art. get Airbnb, you get like.
Oh, I think.
Oh, no, that would be cool. Like a little high-rise apartment. No, there's plenty of hotels there. Some hotels in Iceland, but I just prefer in general, like. Stayed one time at the. Like,
Yeah, it's one of those.
We get done. Kind of something they started to recover. Yeah, they really like the reason to visit that there during the summer is it's kind of the off time for people who don't like gamble. Weather's starting to change and like they really embraced the beach there, which I appreciate. Like Vegas when I was growing up was just like awful.
Oh, really?
Yeah, so yeah, I didn't have any good music. It wasn't very large, like, you know, all these like nice clubs that have come in. They came in the last like 20 years.
Oh.
You'd be like.
Yeah. But now you have all these people who would, you know, make it kind of like a visa in the US. That's much better.
Yeah.
Looking at that clock, wondering when this time is.
Yeah.
How far do I- Let's try to go a little bit.
Yeah, these are always supposed to be good.
It's like those pictures you were showing. Yeah, you can go wherever you want. Are you wearing that video? No one is saying.
Yeah. Yeah.
Only 50% of you picking up physical land.
Well, and also the mid.
You had-
I'm sure we're gonna have.
I don't know when we started, so I don't know when to stop them.
Oh. Some give up visible land.
We'll give them 2 more minutes.
Everybody giving up. You know, Tony, you might have invited my roommate.
That's crazy. So. Oh, really? Oh, nice. Were you, camping? Not good.
Oh, yes.
Yes, like, no, you really took it.
It's almost like the book is like where I get.
Remember,
Do like 1 more minute and then we'll talk some more and then we'll do more of this. Does that sound good?
always giving up.
Oops. Okay, folks, you ready? You're gonna transition back into me talking about it. Okay, we can finish it at the end too. There might be extra time, might not. But there's a lot of atmospheric stuff to talk about, and we haven't even gotten to the other planets in our solar system that have atmospheres. So we're gonna talk really briefly about, we talked a little bit about weather. A tiny bit, maybe not as much as you'd like. But we're gonna talk about climate. And we're specifically gonna think about how a planet gains and loses atmosphere. And we're thinking about this in the context of our nearest neighbors. We have two of them. Right, Mars and Venus. Which one's closer to the sun? Venus, okay, good. And which one's farther from the sun? Good, okay. So this is an artist's conception of what Mars used to look like. On the right-hand side, there was certainly evidence that there is large standing bodies of water, including potentially lakes, maybe an ocean, depending on who you want to argue with, but certainly rivers that were running for many millions of years. We can see all of the geologic evidence. So somehow you started with something that looks very similar to this on the right-hand side, and you end up with something that looks like this, a barren, desiccated landscape that has nothing on it. And why would we care if it looked like that?
We don't wanna end up like.
Well, we don't want to end up like that, that's good. And also,
Yeah, like,
could have life. Those are two really important questions, right? When we think about Venus, we want to think about the other way. What are the other ways that we could lose all life? So it's interesting, right? Because our two nearest neighbors have basically opposite things going on. On one side, it's cold, no atmosphere. On the other side, it's hot, too much atmosphere. And we're like right here in the middle, like Goldilocks, right? Okay. Make sense? I keep looking at that clock. I need to take that clock down. Someone take that clock down so that I stop doing it. Okay. So what are the sources? What are the ways we can get atmosphere?
You actually wanna stay?
Yes, please.
Okay.
Because otherwise I'm going to base how much time I have left on that and we'll go forever.
Minutes, same,
No, that's actually not moving forward.
at all?
No, it's just clicking. Okay, so what are the ways in which we add atmosphere to our planet? Volcanic outgassing, good. Anything else?
rotation.
Adding gas to our atmosphere?
What's the faster rotation?
How would they add gas? Volcanic outgassing. Impacts. So stuff that comes from outside could hit us and melt, become atmosphere. Anything else? What's that? Evaporation. So we have a big old ocean. We can add atmosphere by evaporating it. Boom, we did it.
Oh, it's easy.
Amazing. That was a group effort, right? No, it's never aliens. Okay, and you'll notice this is the size here. So most of it comes from outgassing. And the primary constituents are going to be H2O and CO2. You have some N2 and some sulfur gases. We'll talk about why our atmospheric composition does not match this in the proportions that it comes out of the earth. The answer will surprise you. And then this piece here is evaporation and sublimation. So you might have ices on the surface and they melt. You have water, lake surfaces, right? And those melt and they become the atmosphere. You have impacts by micrometeorites, energetic particles. This is a very, very small contribution today, but historically, this was a really important contribution. And in fact, we think most of the water that you're now drinking probably came from icy asteroids. Weird, right? Okay. So here's a question. Why did the Earth outgas as much CO2 as Venus? Is it because A, Earth doesn't have as many volcanoes? B, volcanism was only active for a short period of time on Earth? C, Earth outgassed CO2 escaped the gravitational pull of Earth? D, Earth's CO2 never made it out of the mantle? E, none of the above, it did outgas as much. Move your fists when you're ready. Let's vote on 3, 2, 1. Okay, we got some 1s, 4s, 5s, 2s. Anyone want to defend their argument? Yeah.
So since they're both relatively the same size, but probably gonna have the same amount of outgassing. It's just that the Earth had more water. And so more water is, so essentially CO2 likes to be absorbed by water, right? So then the more water you have, so like basically limestone, right? Limestone is absorbed by water. So then we do have the same amount of CO2, but we just made it something else.
Okay. That's a hypothesis. People like that hypothesis? You have an argument? Plants? So plants in limestone, maybe? Anything else? Everyone liked that argument. No one disliked it.
I feel like I picked A just because I thought Earth was younger than Venus, so it hadn't had much time to go through much.
Okay. Okay. Earth isn't younger than Venus. That's okay then. But one thing that is really important when we think about like Venus, and I had this conversation with another student, we tend to think that Earth doesn't have as many volcanoes, that it's not the most volcanic planet in the solar system. And this perception comes from the way that we think about Venus. We think about Venus based on a couple pictures where the surface is yellow and there's a big atmosphere. This is a perceptual problem. Whereas for large swaths of Earth, including the Pacific Ring of Fire, the whole thing is volcanoes, right? There are more volcanoes on Earth, individual, active today than anywhere else in the solar system, obviously, right? So actually, that's not true. Io per capita has more, but we have. Okay, anyway, I'm not gonna fight about it. But between Venus and the Earth, we have more volcanoes, we think. Okay, we also have like a giant crack in the middle of the planet. That's the Atlantic sea force that just like is volcanic trench the size of the whole planet. It's cool, right? You can go visit. You can go visit. Okay. So that was the first one. Is that okay? It felt like a trick, but it's not a trick. And this one says none of it above. It did outguess. Any other votes? Yeah. No one liked this. Because I just explained how it wasn't the case, right? Okay. And no one liked this because we do have CO2 and CO2 is heavy. And I just said that the main byproduct is CO2 that outgasses. So it has to be this. And there is a combination of water, limestone, and plants that make this possible. We'll talk about that in detail. One question we might ask ourselves is the inverse to that. How come Venus don't have plants, limestone, and water? Yeah, but is that a result or is that the cause? That's an interesting question for current planetary scientists. Okay. So this is the main source of large terrestrial planetary atmospheres. What you're breathing right now is the Earth parts, so to speak. But it's not the whole story. Okay. There are also ways to lose. So we talk about sources and sinks. Sinks are ways that it disappears. You have thermal escape from the top of the atmosphere. Stuff is hot, and at the very, very tippity top of the atmosphere, it just says bye, and it leaves forever. Or sometimes it's at the top of the atmosphere, and the solar wind comes in very hot, says bye, and it leaves forever. Some of it condenses into ices, and some of it oxidizes and makes the surface red. So the same process that if you look at the bottom of the ocean, you see the video of the Titanic and all the metals all red and rusted. That is the same process that occurs on the surface of Mars. The whole planet is rusted. Cool, right? Okay. Let's skip over that. I don't care. So let's think about what happened to Mars and Venus. So here's Mars. It has about a 1/6% of the Earth's atmospheric composition. Sorry, I didn't say that right. 0.6% of Earth's atmospheric composition pressure. It's primarily CO2, and it never gets above freezing, almost anywhere. So you have a northern polar cap that's almost entirely dry ice. We'll play with that on Monday. Don't forget, Monday is comet day. We make the comet in class. And then we found that, and we found this multiple times, I think every year, someone says, oh, water from Mars. Because it turns out that's a really good headline and you can get a lot of clicks from that. But the very first time that we saw this was directly under the surface. We just scraped, and right under the surface, under the sediment, is ice. And it's water ice. So cool. There's frozen CO2 here, there's water ice here, and very little scattering. So this is a sunset on Mars from the surface from a rover. What color is the sky there?
Blue, very like.
Kind of blue.
Kind of blue.
Maybe
And-
it's a little green.
Yeah, maybe let's turn off the light so we can see better. Thank you. I like it, right? Yeah, it's boring, right? It's not a beautiful, like California red sunset, right? You like that? We have half of them back now. Thank you. Okay. So there is a little bit of atmosphere, and the question is, how did this happen? So in the first 1 to 2 billion years, the atmosphere, the interior of Mars was likely warm. The planets likely formed all at the same time, and it took about 2 billion years for the interior to fully cool off. While the interior is still warm, you have volcanoes. Okay. So you have this massive volcano called Olympus Mons, largest in the solar system, 20 kilometers tall. You have giant tectonics, cracking of the entire planet, and you have outgassing. Okay. Likely you had a greenhouse effect. So despite it being very far away, there must have been a greenhouse effect. Because currently the temperatures are too cold for liquid water to have existed, but we see evidence for liquid water on the surface. We see running streams, we see like carved valleys from running water. There's nothing else that could have done it. So we know probably had weather erosion. This one here, questionable. This one, very questionable. Very questionable.
Space whales.
Space what?
Space whales.
Space whales. This would not be a whale. This would be like a little microbe, maybe.
Space whales.
No, not whales. Maybe whales, but very unlikely. We'll talk about the evolution of life in probably the very last class. But the process from which you go from multicellular life or from unicellular life to multicellular life takes a really long time. So you probably only had like little baby single cell amoebas for billions of years. Unless you didn't. That'd be amazing, but I don't think that's possible. Okay, so then Mars starts to cool down. Why does Mars cool down again? What's that? Yeah, but why does it start to cool down? Small. The easy answer, Mars sucks because Mars is small. Okay, it cools down because Mars is small. The pea cools down because it's small. Right? The potato is warm because big. Okay. So in fact, Mars starts to cool down, and what happens? There's less outgassing. Good. What's that?
The aliens need to
The aliens got a book it. So they go over to planet Earth. They're like, "What's up?" Now we're human.
like,
That's not science. Okay. What else happens? So outgassing slows down. Yeah.
There's less tectonics and volcanism, so the core stops.
Okay. Other way around. But yes. So the core being less active means less volcanism, right? Means less tectonics. Absolutely. So now you start to see these impact craters piling up and not getting erased, right? Driven by the fact that the core is getting cooler. Anything else? What about surface life? If there wasn't. What? Why does it start to die?
because they're drying out.
Remember what was warming the atmosphere? Greenhouse gases. As the outgassing starts to go down, if the atmosphere is getting lost to space by those ways we talked about before, or if it's condensing because it's getting cold, then that's a runaway process. Because as it gets colder and there's no more greenhouse gases to make it warm, it gets colder still. Condensation gets worse, right? Okay, let's walk through this process in detail. So you lose the interior, probably lose the magnetic field at the same time. And the top of the atmosphere starts to get blown away, just like evaporating. Like you leave water on the pot for too long, and you come back like 6 hours later, and you're like, "Oh shit, all the water's gone." You ever done that? Oh, just me?
Have you?
Yeah, sometimes you get distracted for 6 hours. You sometimes get distracted.
And then your house.
In your house, yeah, and then you're thinking catch on fire. So don't do it. Okay, so you have a cold interior. Now I don't have any volcanism and I don't have any outgassing. I cannot add additional material. I'm only losing, right? So no atmosphere, no protection from solar UV or X-rays. Water gets broken apart. Water that's near the surface is getting dissociated. And the problem is oxygen, fine, whatever, it lives down at the bottom, but hydrogen's light. And it makes its way to the top of the atmosphere and it escapes. But once you lose that hydrogen, you can't make water anymore. You're just left with oxygen. And that oxygen at the bottom rusts the surface and makes it orange and red. Okay? So now you have less greenhouse effect. It's getting colder still. Okay, gases start to freeze out. And we all love the fact that snow is highly reflective and it reflects that light out. Yeah.
How many years does the process take?
Very good question.
Great.
Yeah, this is a subject of ongoing discussion. So when this exactly starts happening, it's probably right away, right? You always have a little bit of loss of atmosphere from the top of the atmosphere. This is ongoing right now, but we don't worry about it here on Earth because we have volcanoes. So it's only after about 1 to 2 billion years when the volcanoes really start to taper off that this starts to pick up in Earth, right? And it's very unclear when you talk to climatological scientists who study Mars when this stopped, except for we have some rocks from Mars. We're like, well, this was hydrated up until some time. I don't know that because I don't like rocks, but they know that and they believe they're rocks. So we think probably 3 billion years ago is when this really started to become a problem. Maybe 2.5 billion years ago, atmosphere starts getting lost in mass. But it's amazing, right? Because if you think about this in detail, the amount of atmosphere you have to lose is essentially going from very current or something similar to this atmosphere that you're breathing right now, right? 1 bar to about 6 1,000ths of that amount, or less than 1% of that amount. And that's all gone. Not in the surface, not trapped under the surface. So anyone who says, let's go to Mars and make it a great place to live is a
Liar.
idiot. Idiot. Okay, they don't know what they're talking about. And we can go into a wonderful part of that. That'll be part of the last lecture too. I've said this for many years and I've gotten a lot of flack, and it turns out, okay. So now we can no longer support liquid water, and so Mars is not a great place to go visit unless you're really interested in Mars rocks. So you're stoked about like picking up some rocks and being a cool geologist, go for it. Don't try to live there. It's a very good planet currently, I think. Okay, here's the picture. Early Mars probably looked like this. Maybe water on the surface. I could draw that in if you want. Atmosphere is coming from all of this outgassing. See the plumes? And you got this nice magnetic field. We know that it had a magnetic field. We see crustal remnant magnetization in the southern hemisphere that came from there being a dipolar magnetic field. And then it just cooled off because it's small. And when it's small, it dies. Okay. All right. If you moved Earth, you moved Mars from its current location to Earth's orbital distance, what would occur? Would the greenhouse effect develop, leading to a pleasant Earth-like climate where we could live, like second Earth, Earthport 2? 2, a runaway greenhouse would develop and Mars would be too hot to live on. C, the polar caps would melt into oceans, leading to a stable climate. D, some increase in its surface temperature, but still too cold for life. Or E, no change at all. Okay, let's get ready to vote. 3, 2, 1. Damn, I really didn't get anyone. What do we got here? What do you think? It's this one, right? No. Damn. Is it this one? Yeah, it's some increase, but not a lot. Not enough to make us happy. Okay. Let's talk briefly about Venus. So these are the pictures of Venus from the surface. They're in black and white. I'll get you the color versions, but they're boring. It's mostly yellow. Shocking. The atmosphere there is 90 times the Earth's in pressure. And the temperature is absurd, very hot, and everything melts. So we try to drive around on the surface, and we have, let's see, that's 880 degrees Fahrenheit. So I think your electronics in your phone turn off at like 150 degrees Fahrenheit. And then they say like, go into warning mode, right? So this melts everything. All of the transistors, all of the electronics that we send, we know we're only going to get for a little bit. And so we say, just send it to us right away and we'll analyze it. And so we're sending 2 missions. I know, okay, don't get me wrong. I love Venus science, but I want to like float in the atmosphere and just like drop little things. They're just really interested in like dropping it on the surface. They're going to be like, we're going to find out more stuff. Believe you, I just don't know what it is. And it's almost all CO2. And if you look at the surface here, kind of looks earthy. All right, if you squint. How did Venus get like this? The answer is something called feedback, and that is not what you provide to me about how great the class is going. This is a science concept, okay? And in fact, you may have heard of the word positive and negative feedback. So positive feedback makes you want to keep going, right? If I tell you that you're doing really well in the class and I'm really proud of you, you want to keep doing it, right? Negative feedback is like, I really hate when you come to class and you make me sad. And then you don't want to come to class anymore, right? Okay, so here we have a different type of process here. If I perturb it in some way, does it accelerate that change? So the words positive here, it's important to remember, don't always mean good. I use that example, but I'm talking about, does it accelerate what's already going on versus does it return it to a stable equilibrium? So I would say this is negative feedback as I pull the ball to the right and I let go of it. Goes back towards the middle, and eventually if there's friction, it'll stop. Whereas if I'm up here at the top of a hill and I press it in either way, it'll just roll down and it'll never come back here. So if I say, you're having a really good day, your day continues to be good. Right? I don't know if I'm trying, okay? All right, so let's think about clouds. I told you clouds suck, right? Yeah. Okay, so let's do both of them. So suppose the cloud cover increases. This is the change. How does the atmosphere respond? So positive feedback would be the new clouds trap more infrared radiation. The troposphere is going to warm. You're going to increase evaporation, which forms more clouds. Oh, and then we all die. It's just cloudy forever. And it gets super hot. Now, of course not. But in fact, over here, you can see a different way of thinking about it. You can say the new clouds reflect light, so there's less at the surface, and now the troposphere cools, which decreases evaporation, which means that the clouds will eventually get decreased. And annoyingly, these can happen at different times. Does that make sense? Okay. Which of the following is not an example, or which of the following is an example of negative feedback? A spooked cow causes a stampede. B, the hotter you get, the more you sweat. C, ice melts, making the surface darker and therefore warmer, causing more ice to melt. D, the rate at which the balance in a high interest savings account increases with time. Ready to vote? Ready to nap? Vote on 3, 2, 1. Ooh, we got all of them here. All right, anyone wanna offer up an explanation? What was the definition of positive feedback? Amplifies the change. So I say to you, you're doing really well in class and you want to come to class more. Right?
A,
You picked A.
because like, a one is like a cause and effect kind of thing, so.
Right, so-
Cow gets
so-
spooked and then it scares all the other cows.
Okay, so does it amplify or negate the effect? See, so even though it's a negative thing, the negative feedback speaks to whether or not it amplifies the process or decreases the process. This is why I use this exactly. The spooked cow here spooks other cows, and this is a positive feedback. Any other examples here?
Well, I said B for the negative feedback, since the hotter you get, the more you sweat, but the sweat is trying to make you cooler.
Oh, interesting. That is a negative feedback effect trying to save your life. Okay. Right? Okay, a fun aside on sweat. We're one of the only creatures that does it a lot. And it allows us to be long distance runners. It allows us to walk for really long distances. And it gives us our original form of hunting, which is just follow something until it dies. Did you know that?
Yeah.
So human beings, they can sweat really effectively and other animals can't. So we don't even have to kill a deer. We just follow it for a really long time and it keeps getting scared, but it can't sweat. And so it runs away from us for a really long time. And eventually it dehydrates itself because it can't sweat and it can't drink and it dies. And we eat it.
Yeah, I heard that, and I was like, persistence.
We're called persistence hunters. Because look at this is not very good for kill. Eh? I can't just jump on something like a lion. So I just walk and I wait and then it dies and I eat it. That was true. Unless it's a rabbit. Rabbits are really hard because they go underground. Okay. So Venus, sister planet or evil twin? It's a sad twin. It's misunderstood. We like twins in this room? Okay, so it's as large as the Earth, probably had outgases, right? Lots of greenhouse gases, and it's a large atmosphere, so it held on, or sorry, large gravity, large planet to hold on to its atmosphere. That ends up being a little bit of an issue for it, because this leads to a massive greenhouse effect, which leads to increase in surface temperatures, accelerated by the fact that you're close to the sun. Right? And then you have a real bad problem. So you start with high temps. And if you did have oceans on the surface of Venus early on, which a lot of people think would have happened, we said that water is a really effective greenhouse gas. So now you turn it into steam. Uh-oh. And that leads to more greenhouse gases, which leads to higher temps, which leads to more steam. And that keeps happening. And the temperature starts skyrocketing. Okay, so let's say you had your boat down by the Venus like marina or whatever. At first, all the water in the ocean starts to go down slowly. Like, well, this sucks. I gotta move my boat, move it to lower and lower location. Then the water disappears completely, and then your boat gets on fire. So have a bad day, yeah. Okay, so this is a positive feedback process, even though it's a bad thing that happened to your boat. Okay. And this is what it looks like. The temperatures, down here is where you think you could probably live. That's not so bad. We have like a balloon up at like 100 kilometers. Kind of like hang out. That's where you want to be at, except for this is sulfuric acid.
Yeah.
So maybe not great. Okay, so this is a version of an extreme greenhouse effect. And it's really important to remember, whenever we think about planets that are outside of our solar system, And we'll do this towards the end of the semester in detail. If you hear someone talking about a planet, right? Our two nearest neighbors, it's right? So we really got to think very carefully about whether or not there could be other things living there. Okay, so where does an ocean's worth of steam go? We talked about dissociation of water. We break it up.
Whenever we talk about planets and we talk about the distance from the sun, has the sun been the same size since the creation of all the planets? Was there a time where at some point Venus was at the Goldilocks zone distance away from the sun?
I don't like that question. Very good question. And in fact, it's very likely we have something called the early faint young sun paradox. Because the sun early on was fainter. And yet Mars definitely had liquid water on the surface. So there's a huge paradox in science that people don't want to talk about. Well, they're talking about it, but not to the public. And in fact, this is a major source of interest, right? Because the sun itself evolves with time, changing its luminosity. Over our time periods, it's the same. But in 4 or 5 billion years, it'll become a gas giant. A supergiant, a red giant. And Mercury gone. It'll just eat up Mercury. Venus probably gone, and Earth knocked off course. So it's a very good question, because when we think about stars and we compare them to other planets, their exact amount of light that they're giving off and what types matters whether or not you would have a planet that you could live on. Okay. This is how you lose an ocean worth of steam. You break it up, you send it to the top, and it leaves. I'm not going to ask you that, so I don't have time. So why didn't Earth suffer the fate of Mars or Venus? What? Water atmosphere? And? Well, it has a magnetic field, right? All of those things probably happened at Venus too.
Would it just be like the distance?
Bada bing, bada boom. Okay. So we're going to talk about the climate stability, which is due to the CO2 cycle. Water is certainly important, but the presence of water on the surface in a form that matters is due entirely to distance from the sun. Because if you're too close, we talked about for Venus, you get steam. If you got steam, you're happy. Okay. Yeah, any questions, comments, concerns? So tomorrow, if it's like this, well, that's bad. But it's not raining, which is good. So if you wake up and the sun's out, it's beautiful, and then you get to lunch, the sun's out and it's beautiful, and you get to dinner, and the sun's just going down and it's beautiful, we're gonna be at the observatory. It will be cold. I think it's like 45, 50 degrees. So don't freeze, please. Tomorrow, yeah. 7:30. 7:30. 7:30, 8.
45.
7:45 p.m., not a.m. Okay. Yeah. Questions, comments, concerns? You can keep them. You can either, if you haven't finished them already, we'll finish them on Monday.